Yes, we do define as a polynomial. What is its degree? Degree 0, right? Because 5 can be thought as a 5x raised by 0. But x raised by 0 is just 1. 5 times 1 is just 5. So it's a degree 0 polynomial. With polynomials, we can add them. We can add subtract-like terms. Right? What are like terms? Like terms have the same variable with the same exponent. Right? Let's see this example of a squared plus 7b squared minus 6a squared. We see this 1a squared, negative 6a squared are like terms. So we can combine those two by performing the operation with their coefficients. Coefficients means a number before them. So number before a squared is 1. Number before negative 6a squared is negative 6. So get a 1 minus 6, which is negative 5. So combine those trinomial, get negative 5a squared plus 7b squared. Anyone has any questions? Okay, let's see this one. We have this trinomial, we have this trinomial, we want to add those two trinomials. So what do? We look for like terms. 7y squared plus 4y squared, that's 11y squared. Negative 2y minus 8y, that's negative 10y. Positive 9 minus 7, that's positive 2. And we can subtract two trinomials, right? We want to subtract this one from this one. So the second one comes first. So we can write as p squared plus q squared minus 7p squared minus 2pq minus 2q squared. So p squared minus 7p squared, that's negative 6p squared. Okay. Then q squared minus negative 2q squared. Negative, negative become positive. It become plus 2q squared. So 2q squared plus q squared, that's a 3q squared. Now lastly, we have this negative 2pq become positive 2pq. Positive 2pq. Right. Anyone has any questions? Now we try the other way around. We use 7p squared minus 2pq minus 2q squared minus p squared minus q squared. So 7p squared minus p squared, that's 6p squared. Negative 2pq minus no like terms stays to be negative 2pq. Then negative 2q squared minus q squared, this is a negative 2q squared minus q squared, becomes negative 3q squared. So the answer we have 6p squared minus 3q squared minus 2pq. Anyone has any question? Does order matter when it comes to adding or subtracting like terms? Yes, order matters when, just be careful with the negative. With plus, you can switch the orders, but with minus, you cannot switch the orders, right? You see, if we have minus PQ, we just have to do 7p squared minus p squared, right? Minus 1p squared. And we cannot change this order, right? Because with a negative sign, you cannot change the order. With plus, yes, right? Plus, we could do p squared plus q squared, that equals to q squared plus p squared. Okay, then we go to polynomial functions, right? If we put f of, what is a polynomial function? Let's see, this is standard form. Only x is variable, right? We have f of x equals to some number multiplied by x raised by n's power plus some number multiplied by x raised by n minus 1's power, so on and so forth, right? Some number multiplied by x squared, some number multiplied by x, then a constant. So this is a standard form of a polynomial functions. And the polynomial of degree n start from 0. It can be 0, can be 1, can be 2, can be 3, so on and so forth. Right? The first one with n's power is called a leading term, and the number before it is called a leading coefficient. Let's see this example. F of x equals to 3, right? Constant function, polynomial of degree 0. 2x minus 1, polynomial of degree 1, or linear function. 3, polynomial of degree 2, or quadratic function. Just like we can add subtract polynomials, we can add subtract polynomial functions by combining like terms, right? If we have f plus minus g of x, that's equals the function f plus or minus g of g function. Now let's see this. Oh, okay, just make sure. So two functions here. Function f is a quadratic function, polynomial degree 2. Function g is also quadratic function or polynomial degree 2. So what is the difference? Difference from before, we see the polynomial expression can have different variables in it, but with the function, we only have one variable. Because we're dealing with single variable functions. In the future, when you keep learning in calculus, you may encounter something called vector calculus. You have more variables. But at this moment, we only have one variable, x. Right? So f is defined this way, g is defined this way, and we want to find f plus g of x. We just add like terms. So 5x squared plus negative 3x squared becomes 2x squared. Negative 8x plus x, negative 7x. 4 has no like terms, it's just 4 by itself. We can do subtraction of two functions, two polynomial functions, right? 5x squared minus negative 3x squared minus negative become plus. So 5x squared plus 3x squared becomes 8x squared. Negative 8x minus x. Well, that's negative 9x. 4 has no common like term, so it's just by itself. Okay, if anyone has any question, feel free to stop me at any moment. F of x equals x squared is the most basic quadratic function, right? If we sketch the graph, we give a couple of values of x, then we get f of values of x picking. We get some points. With some points, we can draw this symmetric graph to y-axis. With functions, we like to use some terms. The one term is called domain. What does domain mean? Domain means what kind of numbers work for this function, or what kind of x values are allowed. to evaluate the function. For this function is a polynomial function, so all real numbers are allowed. With polynomial functions, the domain usually is from negative infinity to positive infinity, interval notation. So all real numbers means if we use set notation, this is set notation. Means a number multiplied by itself, it can never be negative. Use interval notation, we see goes from negative infinity up to positive infinity. Another term is called range, right? Range talks about the function value. So domain is for x value, for the independent variable x. Range is for the function value or the y value. Right? We could see this x squared. All y value does not appear below x-axis. That means the y value will never be negative. So how do we represent that? We represent will never be negative with the interval notation goes from 0, including 0, up to infinity. So what is the domain of any polynomial function? All real numbers, okay? We use interval notation. We use this notation from negative infinity up to positive infinity, all real numbers. What about linear function? Well, linear function is a polynomial degree 1. So domain is all real numbers. What's the domain of linear functions? All real numbers. Yeah, if you plug in any number, you will get this. If you right, you only get this. You evaluate. So linear function is polynomial degree 1, and its domains are real numbers. So what about the vertical lines? Vertical lines is not a function. Remember that, right? Has x equals the value. It's a vertical line, and its domain is what about its domain? Domain is 2. We cannot talk about function value, right? We can talk about as a relation. A domain only has one member, x equals 2, but the range is all real numbers. This you have this vertical line. X value stays to be 2, but the y value can be anything on the real numbers. So what's the domain of this function? Just x equals 2, right? Just one member in the set. Where function is defined by x cubed, polynomial of degree 3. Domain is all real numbers. The graphic looks like this. So this is a graph of x cubed, okay? You can remember it by raising your right arms up, left hand down. So this means when x approaches to infinity, y value also approaches infinity. Because this goes bigger, 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 x goes bigger, y goes bigger. This other side in the third quadrant, x goes smaller, y gets smaller. So your right hand up, your left hand low. That's how you remember x cubed, the graph for x cubed. What about its range? Its range is all real numbers too, right? All real numbers. What's the difference from the range of x squared? X squared in the range, we will have no negative, right? From 0 up to positive infinity. But x cubed can be negative. So these are all real numbers. So if we use function notation to add, subtract, and find the values at a specific x value, let's see some examples. We have f defined this way, we have g defined this way. If we want to do plus, it's a plus a function f with function g. Then we add like terms, 2x squared, add x squared, 3x squared, negative 4x minus plus negative 2x, negative 6x, positive 3 minus add negative 6, that's negative 3. And then we can evaluate. If we want to evaluate, let's see at 3, right? F plus g evaluation at 3, we just change x to be 3, then evaluate. Then we get a number. We can also subtract. If we subtract, we also get a quadratic with polynomial degree 2. We can evaluate at any value, right? Get a function value. Or we can do g minus f, right? The other way around, the second one minus the first one. We still get a quadratic polynomial of degree 2. Anyone has any questions? Okay, let's see some live applications. So a painter drops a brush from a platform 75 feet high. The polynomial function represents the height of brush after t seconds. So find the height after t equals 2 seconds. What was the plug-in h of 2, right? So every h of 2, so we substitute t into 2, we calculate. So get 11 feet. So after 2 seconds, the brush, the height of the brush would be 11 feet above the ground. This is evaluation of a function, right? Let's see this one. A manufacturer of the latest basketball shoes has found that revenue received from selling the shoes at a cost of $p each is given by the polynomial. So the revenue in terms of a p, price p, is 4p squared plus 420p. A downward parabola, right? A polynomial degree 2 or quadratic equation, or quadratic function. So what do we want to do? We want to find the revenue received when the cost of each shoe is p equals the price equals $90. So we just plug in 90 for p, right? So we get negative 4 times 90 squared plus 420 times 90. Then we'll do the calculation in the end, we'll get 5,400. Pretty simple, huh? Okay, next section we'll talk about the properties of exponents. In the exponential notation, we have a base, we have exponent, right? You see, in this case, a to the m's power, a is base, m is exponent, right? That means we have m of a's multiplying each other, a times a times a times a, m times. First one, product rule. If two expressions have the same base, the relationship is multiplication, then we can keep the base, add their exponents. Same thing for quotient rule, right? If we have one divided by another, this is equals a raised by x minus y, right? In the numerator, the exponent is positive. In the denominator, the exponent becomes negative. Similarly, if we have a quotient rule, if we have a same base but division, we will subtract. Okay, product, we add the exponents. Division, we subtract the exponents. The numerator one subtract the denominator one. Power rule means we have two layers of exponents. We multiply the two exponents. If we have two things, we have A, B inside the parentheses, then raised by power. So the power distribute to each one. Power distribute to A, power distribute to B. All right, so this one, just be careful with it. Sometimes people forget to apply to the first one. So it has to be A to the X, B to the X. Same thing for division, right? If the exponent is outside the parentheses, X has to be applied to the numerator and to the denominator. Zero exponent, anything raised by 0 equals 1. Negative exponent, that means it happens in the denominator, right? If we have 1 over A raised by 3, that can be written as A raised by negative 3. Fractional exponent, if we have a y root of A to the x, we can write as A to the power x divided by y. Any questions? Okay, let's see some numerical examples. So 4 raised by 3, we can be thought as 4 raised by 1, 4 times 4 times 4, right? And each 4 has exponent of 1, so 1 plus 1 plus 1, that's 4 raised by 3. Or 5 squared, that's 5 raised by 1 times 5 raised by 1. 1 plus 1 is 2. Well, a to the 0th power equals 1, a to the 1st power equals 8. A to the nth power is n of a raised by 1 multiplying each other. Yes, question?
Professor, can you hear me?
Yes.
Okay. So good afternoon. I have a question. For fractional exponents, why does it become a square root?
This one, the last one, right?
Yeah.
Okay, you see a raised by x divided by y. The numerator is power, a to the x power. That's exponent. But the denominator y is the index. That's a good question. It's the index. It's like if it's a square root of 2, the index is 2. Does it make sense?
Oh, so like a reciprocal?
Nope. Let's go to the whiteboard. So we use this notation. So a raised by x with this index. Remember the index, if we have a square root of 2, the index is 2, right? By default. But in general, we can use this one. So this one can be written as a raised by numerator is the power, denominator is the index. So this y is called index. Index. What does index mean? Okay, let's think about square root 2. Let's see this equals to 2 equals to x. Square root 2 equals x. What does it mean? That means this. That means something square equals to 2. X squared equals to 2. Right? So x equals square root 2 means x squared is 2. All right, now let's go back to our textbook. So last one. So denominator in the fractional exponent, the denominator is the index, because the numerator is the power. Right. So again, if we have the same base, multiplying, so we add the exponents. That's how we combine them. We add the exponents. Oh, you're welcome. Usually we could see a to the m's power, a to the n's power, a to the m, a to the n equals a to the m plus n. So this property holds for the base has to be the same. If the base are different, we cannot do anything. All right. Right. This use numbers. If you have 3 squared times 3 raised by 3, which is do 3 raised by 2 plus 3, which is 3 raised by 5. Let's see those examples. But b to the 5th power, b to the 3, right? That means 5b multiply each other, 3b multiply each other. So how many in total? Is a of b multiply each other. We can write as b to the 8th power. If we have a squared, b to the 4th power, different base, then multiply by a cubed, b raised by 5. We have to look for the same base, because we can combine the exponents if they have same base. So that becomes a to the 2 plus 3, which is 5. B to the 4 times b to the 5th, that's b to the 4 plus 5 equals 9. Let's see this one. The first one is negative 5x raised by 5, y raised by 7. The second one is 3x cubed y squared. We just multiply the numbers with the number, the term with the number with the same base with same base, right? So negative 5 times 3, negative 15. X raised by 5 times x cubed becomes x raised by 5 plus 3, which is 8. Y to the 7th power times y squared becomes y to the 7 plus 2, which is y to the 9th power. Let's see this one. We have 2uv multiplied by negative 3u cubed, z to the 5th power. 2 times negative 3 and negative 6. V is all by itself, is a v. U, we have u times u cubed. That becomes u to the cube plus 3, which is u to the 4th power. Z to the 5th power by itself, right? Just carry z to the 5th power. Anyone has any questions? Okay, quotient. Again, a to the m divided by a to the nth power. We write that as a raised by m minus n. Okay, same base, quotient, subtraction. So a to the 0th power is always 1. A to the 4th power is always a. So let's say 2 raised by 5 divided by 2 raised by 3. We could just go 2 raised by 5 minus 3. A to the 5th power divided by a to the 3 equals a to the 5 minus 3, which is a squared. variable. Okay, let's see this one. Let's see, we want to find a quotient of 5k raised by 4 and 6k raised by 3. That's 5k raised by 4 divided by 6k raised by 3. Or 5 divided by 6 is just 5 over 6. Then k raised by 4 divided by k raised by 3 just becomes k. So this can be written as 5k over 6 or 5 over 6 of k. Let's see this one. 6k raised by 9 divided by 2k raised by 3, same base, kk. 6 divided by 2, that's 3. K in the numerator, k in the denominator, same base, so we subtract the exponents. Or 9 minus 3, that's 6. So we get 3k raised by 6. Simple. Well, let's see this one. We have x raised by 5, y raised by 7 in the numerator, x raised by 3, y raised by 5 in the denominator. We look for same base. X raised by 5 divided by x raised by 3. That's x raised by 5 minus 3, which is x squared. Y raised by 5 divided by y raised by 5. Y raised by 7 divided by y raised by 5. That becomes y raised by 7 minus 5, which is 2. Next one, with a u to the 4th power, w to the 5th power, divided by 3u cubed, w squared. So first we do number a divided by 3, this is a over 3. U to the 4th power divided by u to the 3rd power becomes u to the 4 minus 3, which is 1. W to the 5th power, w to the 2nd power is a w to the 5 minus 2, which equals 3. Yes. So since we can divide, yeah, we can divide a over 3, we just rewrite it, right? Just write a divided by 3, a over 3. Just do a over 3. Maybe I should, let me see. Oops. Wait. Okay. Just a over 3, uw3. But negative exponent, sometimes we may get negative exponent, right? We use a raised by negative n to mean 1 over a to the nth power. Okay, that's a definition. That's definition. So 1 over a to the nth power is a raised by negative n. But if the negative exponent happens in the denominator, so that becomes 1 over a to the nth power, which is just becomes a to the nth power divided by 1, which has become a raised by n. All right. So if the negative exponent in the denominator, we flip it to the numerator, become positive exponent. If the negative happens in the numerator, we flip down to the denominator to have a positive exponent. 2 to the negative 3 is 1 over 2 to the cube, is 1 over 8. 1 over 2 to the negative 3 will be 2 raised by 3, which equals 8. Right? 1 over 4 cubed, which is 4 raised by negative 3. So that's what negative exponent do to the expression. Let's see this one. We have u to the 4th power in the numerator, u to the 9th power in the denominator. So that's u to the power 4 minus 9, which is u to the negative 5 fifth power. So that equals 1 over u to the 5. This one, 2 divided by 12, that's 1 over 6. Then u cubed divided by u raised by 11. That's u raised by, if we want to bring to the numerator, we do 3 minus 11. We get a u to the power negative 8. The negative 8, that means in the denominator. So u to the 8th power. Well, then w cubed divided by w squared is a w. All right, be very careful with this. You see the u term, u to the 3, u to the 11, right? You could think, because 11 is bigger than 3, you could think, okay, that's 11 minus 3, which is 8. But it stays in the denominator. Let's see this one. 3 divided by 27, that's 1 over 9, right? Because 3 goes into 27 9 times. X raised by 10 divided by x raised by 11. Well, the denominator has a big exponent, so that just means x raised by 11 minus 10 is 1. And y, we have numerator y cubed divided by y squared, so that's just y. Right? Then we have z squared divided by z, so that's just z. Any questions? Okay, keep moving. If we have 2 layers exponent, right, a raised by m, then again raised by n, we just multiply the 2 layers of exponent. The a equals to m times a to the power m times n. Let's see this example. We have 3 squared. When the term or variable does not have an exponent, we just think it's 1 or it's itself. Yeah. Right, if it's 1x, usually just x. Okay, so we want to see this equals to 3 raised by 2 times 4, which is 3 raised by 8, right? Because 3 squared raised by 4 means 3 squared multiplied itself 4 times. That means 3 raised by 4 2's adding together. So it's 3/8. Okay, let's see this one. X raised by 10, then raised by 2. We'll just do 2 times 10, that's x raised by 20. X raised by 10 by 2 multiplied by x raised by 3 by 2. So the first one is x to the 20th power. The second one is x raised by 2 times 3 is 6. So in the end, you'll get x raised by 26. See this one. This one will have negative exponent in it. So x raised by negative 3, then raised by square. Then x raised by 4, then raised by negative 1. Well, first, let's just multiply these 2 layers of exponents. So that becomes x raised by negative 6 times x raised by negative 4. Well, we know negative indicates goes to the denominator, right? Well, we can add those two. We add those two, we get x raised by negative 10. So this means we can write that 1 over x raised by 10. Okay. Any questions? If the exponent appears outside the parentheses, That means the exponent has to distribute to everyone inside the parentheses. Right, so a, b, parentheses, raised by m, that means we have to do a raised by m, b raised by m. You have 2 times 3 raised by 3. That's a 2 to the cube times 3 to the cube. So 3 is distributed to both members. In this case, 2 times 3 raised by 3. Or we can multiply first, right? Multiply, we get 6 raised by 3, we get 216. Okay. Anyone has any questions? Okay, let's see those examples. Inside the parentheses, we have x raised by 3, y raised by 4. Outside the parentheses, we have square. That means this square has to apply to 3, has to apply to 4. Right? Well, the literal meaning is this one multiplies itself, right? Multiply with itself twice. Then we can do product of same base. So that's x raised by 6, y raised by 8, because 4 plus 4 is 8. But another way of doing is just distribute this 2. Right? 2 times 3 is 6, 2 times 4 is 8. So we have x to the 6th power, y to the 8th power. Excuse me. Let's see this one. 3x raised by 4 raised by negative 1. Well, raised by negative 1 means 1 over, right, the thing. So that means 1 over 3x raised by 4. So let's see this one. The numerator will have x raised by 3, z to the power 4 over 2. Then all of them raised by 3. That means we need to distribute 3 to x, to z, and to 2. To x is not 2, because 2 appears in the denominator is half. Right? So we do 3 times 3 is 3 times 4. So 3 times 3, we get x raised by 9. 3 times 4, we get z raised by 12. Then the denominator, it just becomes 1/8. We require the denominator not to be 0, because in mathematics, we don't deal with denominator to be 0, right? So if this quotient inside parentheses, the exponent happens outside the parentheses, we need to distribute m to the numerator and m to the denominator. So we get a to the mth power divided by b to the mth power. Use this example. We have 4 over 3 raised by 3. That means we need to do this 3 times. Or we just do 4 raised by 3 slash 3 raised by 3. Then we do the calculation, which is a 64. I don't know why I didn't finish. 64 divided by 27. Let's see this one. Numerator is c raised by 4, denominator is a raised by 9. Then parentheses raised by 2. So we need to distribute these 2. We multiply 2 with 4, multiply 2 with 9. So that becomes c to the 8th power divided by a to the 18th power. Negative exponent for fractions. So inside we have c to the 4th power, a to the 9th power. The outside is negative 2. Okay. For this, we just flip over. If it's a fraction with a negative exponent, we just flip over the numerator to the denominator, flip the denominator to the numerator. So you see a to the 9th power is in the denominator, now in the numerator. C to the 4th power in the denominator, now in the numerator, in the denominator, and raised by positive 2. Raised by positive 2. Then we distribute these two to the numerator and to the denominator. So we get a to the 18th power divided by c to the 8th power. So this one needs to be memorized, okay? A divided by b raised by -1. That means we just flip numerator and denominator. So we get b divided by a raised by 1. Well, raised by 1, we just don't want to write raised by 1. Anyone has any questions? Let's see this one. X raised by 4, y raised by divided by y raised by 3. Then outside the parentheses raised by -1. So that means we want to switch the numerator and denominator. So y raised by 3 now in the numerator, x raised by 4 now in the denominator. And that's it. So if we raise by -1, we just flip the numerator and denominator. Well, let's see this one. Well, 5 times at p to the 4th power, q to the 3rd power, p divided by p to the 5th power, and q raised by -1. So we could simplify first, right? We could simplify first. Or we could just do, because it's raised by -1, let's just flip the numerator and denominator. So the denominator became numerator, the numerator became denominator. Then we can simplify from here. Oops. P to the 5th power, p to the 4th power. So the denominator, and this 5 is gone, right? It's just p in the numerator. And q in the numerator, q cubed in the denominator. So just simplify one term. The denominator becomes q squared. Q squared. Right? So this is p equals to p over 5q squared. Or you may think, oh, I can simplify first, then flip over. That's fine, all right? You simplify inside first, then you flip over. When you simplify inside, you get a 5q squared over p. Okay? And with -1 raised by -1, you just flip over the numerator and denominator. All right, let's see this one. This one we have 3, the numerator will have 3x raised by 5, t raised by -3, divided by 2 times x raised by 7t. Then outside the parentheses raised by -2. So one way we could do, we could simplify inside first, then apply -2 power, or we just switch the numerator and denominator, change the -2 to be a +2, right? So denominator become numerator, numerator become denominator. So no more -2, but +2. Then we could distribute these 2 power to everyone. So 2 squared is 4. S raised by 7, then squared, that's S raised by 14. Then t squared. The denominator 3 squared is 9. X raised by 5 now becomes x raised by 10. T raised by -3 now becomes t raised by -6. Right? Then we see, look for terms. So we have x raised by 14 in the numerator, x raised by 10 in the denominator. That simplifies to be x raised by 4 in the numerator. Then we have t squared, t raised by -6. So we do 2 minus -6. That becomes t raised by a in the numerator. This one is pretty tough, huh? Anyone has any questions? And of course, this can be written if you want. this can be written as this. Oops. We can write as s raised by 4, t raised by a on the side. Raised by let me see. X. Right. You can write this way. You can write 4 over 9. Oops. I only need a 4 over 9. Right. 4 over 9. Doesn't go. Okay. I can write the numbers, right? 4 over 9. Then s raised by 4, t raised by a on the side. Well, let's see this one. Should I let you try it? Okay, you try with your homework. All right. Let's see this one. Let's see the next one. Pretty complicated, right? We have this with parentheses. We have 3 things with parentheses, then with power. Let's just deal with one by one. So first parentheses, we have -4 x raised by -3, then raised by 3. Let's just distribute this power 3 to everyone. So -4 raised by 3, that's -64, right? Then x raised by -3, then raised by 3, -3 times 3, that's x raised by -9. And this one, 5x to the 5th power squared. So I have 5 squared, 25, x raised by 5, then squared becomes x to the 10. The denominator, -2, x raised by 13, raised by 3. So -2 raised by 3, that's -8. Then x raised by 13, then raised by 3 again. 13 times 3, 39. So denominator is -8, x raised by 39. Now maybe we multiply the numerator first. Oh, actually we can simplify, because the -64 and -8 can be simplified, right? Because the -8 goes into -64 8 times, so that becomes 8. 8x raised by 9, 25x raised by 10, then 8 times 25, that's 200. X raised by -9 times x raised by 10, add the exponents, that's just x. For denominator, we have left with x raised by 39. Right, so then x simplifies one of the x in the denominator, so the answer is 200 divided by x raised by 38. Okay, so apply, so question like this, apply the outside exponents first. Anyone has any questions? Okay, so I leave the last one for you to try. Well, everybody try this one to see if we get the same answer. Okay, everyone, let's try this one. So I'm going to do myself too, okay? Okay, I got it. If you have it, type in the chat. Okay, let's do it together. I'm going to use this one, right? So first I apply this square, right? So 3 squared is 9. M to the 5th power squared becomes m to the 10th power. C to the 3 power square, 2 times 3, 6. Okay. Then denominator 5 square, 25. Then p to the power negative, oops, to the power negative 4, right? Because 2 times negative 2, that's negative 4. Then on the side, I have 3 to the 4th power. 3 times 3, 9. 9 times 9, 81. P to the power 4 times 4, 16. M to the power negative 20. Right? Because 2 layers, I have to multiply them. Then that equals to, so p to the negative 4th power. Then, because negative in the denominator, we'll flip to the numerator. Right? Then we have p to the 16. You see that becomes p to the 20th power. The numbers we have 9 times 81. 1 times 9, 9, 720, so 729. So the numerator I have 729. 729 divided by 25 for the numbers. Okay. Then we have p to the 20. For the p to the negative 4, flip to the numerator, p to the 4, then times p to the 16, that's p to the 20. Then m, oops. What about m? M to the 10th power times m to the negative 20 power. So that becomes, so m in the denominator, m to the 10th power in the denominator. Then we're left with the c. So c to the 6th stays in the numerator. So that should be the answer, right? 729, p to the 20th power, c to the 6th power, divided by 25, m to the 10th power. Anyone has any questions? Okay, that's all we have to cover today, the exponents. And this weekend, you have to take the exam 1. All right, exam 1 is already open. No, I mean, it's going to open tomorrow, May 9, actually, tonight, May 9, right after May 9. So which means you can start tomorrow morning. And it will end May 9 on Sunday night. So you have 2 days, you have exactly 2 days to do exam 1, all right? So once you start, you have to pick a 2-hour slot to do it. So these 2 hours, you can focus on it. And yeah, once you start, you cannot pause. Once you start, you have to finish in 2 hours. Anyone has any questions? I'm going to stop recording this.